looking at sharding. So there's this inherent inefficiency in blockchains, where if you have 1,000 miners, right, they all have to run every contract. If you have 6,000 miners, all 6,000 have to run the contract. That will just cost 6,000 times as much electricity as running them on one machine. There's no way around that, right? You have 6,000 machines doing the same thing, that's going to cost you some electricity. And then there's a lot of communication and lotteries and blah, blah, blah. But that is like the inherent inefficiency. And you don't want 6,000 of them. There's this thing here going on. In general, as you get more nodes in the network, security will grow and efficiency will drop. But security will grow something like this here. It will level out at some point. After a few thousand nodes, you really don't need more of them. So as you add more nodes, you just get more and more inefficient, but you don't really get more secure anymore. If you have too few, if you have like 60 nodes or 2 nodes or 3 nodes, you're not secure, right? So there's also a lower limit on how many nodes you want in your network. So I mean, because of this inefficiency thing, you have to pick again, right? Either you pick a big network and you're slow, or you pick a small network and you're very, very efficient, right? I mean, for sure this time you have to pick, right? So which one should I pick? Fast or secure? I'm going to trust the audience this time. Yes, I'll take both, thank you. So let's see how we do that. So what you do is sharding. The first idea is sharding. So what you do is, if you have like, let's say 6,000 nodes, you're not going to run one blockchain like up here with 6,000 nodes. You're going to break it into 100 blockchains with 60 nodes in each, for example. Okay? Now we have 100 blockchains. There's 2 effects on efficiency here. Each of them is smaller, so it will actually be faster, let's say 10 times faster. And you have 100 blockchains, right? Each of them 10 times faster, so the overall speed up ideally is by a factor 1,000. That's quite something, right? You're using the same resources, but you're putting 1,000 times more transactions through per second. So that's the base idea. Well, then we should be, but wait. We can tolerate 1/3 corruption, right? Now, if you have 60 in each shard, 33% of 60, that's 20. So now it would only take 20 bad nodes out of 6,000 to break the system. Is that what you're designing? Because that's really bad, right? I mean, for sure there will be someone that will be able to add 20 bad nodes. Well, not completely, and we'll now get into probably the most complicated part of this thing here. We'll do something, we'll add just another layer. Whenever you're stuck, just add another layer, right? We're going to have something here that's called the control chain. And on top of it, it will be running a lot of these shards here. Each of these will be very, very efficient and therefore potentially insecure. But we'll have the control chain underlying here, which will be very secure and slow, but kind of hedging the security. So the way it works is as follows. So the control chain, the big one down here, that will be implemented by all parties, say 6,000 nodes, using the design I already showed you. All the bells and whistles, partial synchrony, finality, So this will be extremely secure. It will be slow, but it will be very secure. But because it's slow, I mean, we'll just make sure it doesn't handle too much data. So we just make sure it only handles a little bit of control data, few transactions per second. And then what it will do, it will take the 6,000 nodes and then randomly assign them into shards. 16 each. And then it will help these shards with finalization. So they don't have to finalize themselves. It will take care of them. Basically what they'll do is just post back on the control chain when they finalize a block. So they don't have to be secure enough to finalize. They will use the underlying very secure control chain for that. And then it's all these shards up here that will do the actual transaction. So if we zoom in a little bit, it will look like this. We'll have a very slow control chain here, not handling very much traffic. It's just talking to the shards, and then it's the shards here that's taking the bulk of all the transactions, and then talking, via the peer-to-peer network. This one is very slow, but handle little data. These are very fast and handle a lot of data. So there's a number of design principles in play here. First of all, we took the control chain and implemented by this very, very secure 6,000 nodes thing I already showed you. That's obvious. That's a no-brainer, right? Because this one is like the key part of the design. So just make it as secure as you can. Okay. Design principle 1. Now this thing is slow. And as I said, we can handle that and just make sure it doesn't have to handle a lot of transactions, right? It's just, keeping track of, are these shards alive, basically. That handles, that gives us security and speed at the same time by having then delegated to the shards. And then an important thing is we have these shards here. We have the control chain do the finalization. And that means the control chain needs to stay below this 1/3 corruption, otherwise it can't finalize. But the shards not. Each of the shards is just going to be a Nakamoto-style blockchain. So they can tolerate to just stay below 49% corruption over long enough time. Right? So they don't have to actually be that secure, and therefore we can make them smaller. So we can make them size 60 or something like that. So what we will assume now is we have a population of nodes out of which we assume 2/3 of them are good. And then I sample a little subset of them and make that a shard, and I just need that half of those are good, right? That sounds feasible, right? If I have let's say 3,000 nodes, 2,000 of them are good, it should be possible to make a random sample and then get something where most of them are good, right? You start with 2/3, you should not just be unlucky and drop below 1/2. And that's why we can get smaller shards, right? We allow the threshold to go down by saying the shard is not supposed to do finalization. So I can sample from a lot of good and just get a little bit of good, and that should allow us to get a reasonable shard size. Did I lose? No. There is a problem with that. No. So the intuition is wrong here. So here's a puzzle. So let's say you do that. You have, let's say, 30,000 nodes. 20,000 of them are good. Okay, 2/3 of them are good. Now you sample at random m of them. And you want to have a good guarantee that at least half of the ones you sampled are good. And let's say small. We say with good probability means except with some very small number. This is what cryptographers consider small. 10 to the minus 180, for example. It means even if you do it all the time, which you sample shards all the time, for 100 years, it will never happen. Okay? How many should you sample for this to behave? Anyone would care to give a guess? Anyone know what that is? It's a guy thinking, but it's a particular guy. Do you know what that thing is? Yeah, that's Kasparov being beaten by Deep Blue. Anyone remember the year that happened? 1979. So that's the shard size you need. That was the hint. So you need to sample close to 2,000 nodes to be sure that with good probability all of them are good, right? So that means we came from a shard size of 6,000 down to 2, and we sampled right from 6,000, and now we have a shard size of 2,000. I mean, that is certainly not going to be worth the effort, right? I mean, that's a huge shard size. It's kind of mind-boggling that this is what you need, but thanks to Christian, I know it's correct. No, he did the computation yesterday. I mean, if it's not correct, you're in trouble. You have to redo the entire talk. Oh, it's correct. I checked in. But we can handle this. So let's take another look at these 49. So we need at most 49% corruption in these shards. It turns out that it's 49 is not 49. So it turns out that, security in general for blockchain means it's live and safe. Live means it's actually doing something. It's putting out blocks. Safe means that the parties in the shard are agreeing on what the blocks are. That's the safe part, okay? It has to do something, and people have to agree. And the real restriction is that if you have something that's live against L% corruption and safe against S% corruption, the sum of these have to stay below 100. Now, of course, that then means, right, if you really insist, as most blockchains do, that they're the same, they both have to be like 49%, right? So you just pick one of them and say, if the corruption is below 49%, my blockchain is doing something and it's doing the right thing, right? But we can be smarter than that. We can, for example, just imagine, for example, in the committee, we say everyone have to sign off on the block, okay? So let's say we add a mechanism like that, and now and then the committee, now and then the blockchain, every miner in the shard have to sign off on something and then play it back on the control chain, right? Or 99% of them, right? Then we would now have a blockchain that's secure if just 99%, I mean, if you have at most 2%, 1% corruption, let's say, right? But it will also very, very easily deadlock, right? Let's say 3% of the nodes crashes. Now you can never get 98% signatures, and it just stops, right? But that might not be a problem. So we do that. So we start up in an initial situation. We start up with a shard size of, let's say, 60, but then we insist on having safety 98%. So it means if up to 98% of the nodes are corrupted, that's all but one, my blockchain is still safe. And we do that simply by saying everyone have to sign off on the block to finalize it. And now if a single one of them crashes, the chain will deadlock. But since it's the control chain that's doing finalization for us, since we're reporting back to the control chain to finalize, the control chain will notice this. It sees a shard that stops having a heartbeat. At some point, for several minutes, it's not finalizing anymore. Then it will kill it, and then it will spin it up again with a bigger size. So there's some kind of corruption going on. So for example, it could then spin it up with, say, liveness 10%. I can tolerate 10% crashes and 89% corruption. That will give a larger shard size, 221. This one Christian didn't do. I did this one, so that's probably wrong, but we'll get it right before we implement it. And then even if 10% of those are kind of corrupted, if there's actually a bad attack going on where 10% of the network is corrupted, I mean, you could just take the full step up and say, now, I mean, fuck it. I just spin it up with 4949. Go to full size, one full shard size. We are under attack, so we slide back in a safe situation, right? But you bring yourself into a position where when things go wrong, it's only the liveness. You never do something wrong. And liveness you can monitor. We have the control chain, which is very secure. And then you just bring the shard down, bring it up again, right? So I think that's, I mean, if we just zoom very, very quickly in on one shard, then it will look like this. The shard here is handling the bulk of the transactions, goes directly to the peer-to-peer layer. There's a launch thing here that launches the shard with size, let's say 60 to begin with. Then there's a thing here we call finalization as a service that's doing the finalization. And then there's a kill process here that's monitoring finalization here, how often it's happening. If it stops, it will kill the shard there, and then it will just get relaunched from this one, but with being bigger. So sorry to the development team, but there will be quite some complexity coming to you over the next year or so with these things. This is still at TRL 1 or 2. So you can again say, I'll take both, thank you. Distribution costs you to be slow, but you don't have to be at full distribution all the time. When the weather is good, you can run with small shards. So that was maybe, I don't know, was that the 6th time or so, and then I think I'm done. Brings us back to the overarching design principle. It says, the network is not perfect. It never will be. You just have to make the very best of it, and you have to open your tech and your science to what the network can show you. And sometimes it's terrifying, and sometimes it's incredibly beautiful, and I'll take both, thanks. And that's a citation by the Concordium tech and science teams. And that's all I wanted to say.